Hello, my name is Afrasiabi. Today is the 27th of July of the year 2018. This is video number 7. This video is dedicated to the future of cancer therapy. I thought that in order to get a basic grasp on the future of cancer therapy, it would be advisable to go back in history and try to find out how the current or modern cancer therapy really started. The history goes back to 1942 when during an accident on a warship going to Germany, the nitrogen mustard barrels got exploded and the crew got exposed to that toxic chemicals, and a lot of crew developed conditions such as aplastic anemia and alopecia and so on and so forth. These are conditions related to death of rapidly dividing cells. So the scientists confidentially started to do some research on nitrogen mustard and later on brought it back to clinic and gave the first patient, who happened to be apparently a pediatric lymphoma patient, chemotherapy with nitrogen mustard. And that is the birthday of the modern era of cancer therapy. Through time, more and more of genotoxic chemicals were discovered and added to in the context of the form of combination chemotherapy in order to improve the outcome. So the thinking was that we should kill the rapidly dividing cells to cure cancer. As more and more understanding of the biology, specifically cancer cell biology, evolved, more and more sophisticated therapeutic agents came into existence. Indeed, perhaps the first targeted therapy that came into existence in around 1970s or so, which was tamoxifen and is still being used, relied on estrogen receptors and antagonizing the effect of estrogen through its receptor. So you could say we came from carpet bombing through nitrogen mustard and combination chemotherapy to targeted therapeutic agents, which you could exemplify to laser-guided missiles, which is hopefully minimizing collateral damage. And as more and more knowledge gathered and evolved around the cell cycle and intracellular communication network, more specific therapeutic agents came into existence. Small molecule tyrosine kinase inhibitors are among such agents, which target the proliferation pathways most of the time. The new generation of immunotherapy, which unleashes the immune system against cancer, has most recently become the hot topic in cancer medicine. And we have become the witness to significantly better outcome in many different kinds of cancers. However, if we look back in the last 76 years as to how we have been thinking about cancer and cancer treatment, it boils down to one statement: we want to kill rapidly dividing cells. However, it turns out that the story of cancer is significantly more complex, and indeed we are now witnessing our limitations as far as cell kill is concerned. And we are basically face to face with looking into our limits the median survival of patients receiving a combination immunotherapy and targeted therapeutic agents many times is modest. The knowledge about tumor mass is telling us that perhaps killing cancer cells might not be the way, and this would open a new chapter in future of cancer therapeutics. Cancer tumor mass is like a society. When you look under the microscope, you might see all the cells more or less the same. However, if you do gene sequencing, whole genome sequencing, microRNA profiling, as I call it and as others have called it, basically measuring or checking the barcode, genetic barcode of cancer cells, you could really see that there are millions of different gene signatures in a tumor mass. So if the surgeon hands you a 5 centimeter breast or lung mass, those cells are not all the same. There are millions of different kinds of cells, and there's a complex dynamic of interaction among these cells. The goal of the tumor mass, if you look into details a little bit more deeply, is survival. And tumor mass has indeed usurped all the evolutionary means that have come into existence in the last 3,800 million years towards its survival. It has become able to metabolically go on fasting and use much less energy and survive and evade the immune system and survive harsh environments and pave its way and move to other territories, so-called metastatic disease. So to recapitulate what I said, cancer tumor mass is like a society which is based and governed on survival, and a society in which any member could replenish the whole society. Imagine in a regular society you have doctors, nurses, scientists, astronauts, bakers, just name it, cook, drivers. Tumor mass could be exemplified to such a society. Imagine you are the cancer doctor and you have given your patient chemotherapy, radiation therapy, immunotherapy, targeted therapy, small molecule tyrosine kinase inhibitors, just name it. And imagine only few cells are left behind. Rest assured, these few cells could replenish the whole society. The astronauts could come back into existence. Doctors, nurses could come back into existence only if for example, the cook, the driver, or let's say a gas station type of employee person is left behind. So this is very puzzling, and I have tried to explain that in my book as to how this could be explained. I focus on location of the tumor cells in the tumor mass, and the entropy barcode of tumor cells. It's not just that tumor cells are programmed to generate the whole tumor mass, it's their location and the fact that not two cells could occupy the same location and not two cells have the same entropy barcode. So this is a complex, at the same time very beautiful biological concept, and that's why in clinic today we are facing a lot of limitations. And so we can see that we have to change our thinking from killing to perhaps conversion of cancer cell into normal cell. And in order to do that, we need to have a much deeper understanding of normal cell. Indeed, I think we have moved ahead of ourselves. I think we need to take one step back and go back to the normal cell division. We need to ask ourselves, under normal condition, what's the mechanism of cell division? What's the mechanism of normal mitosis? Why are single cells dividing non-stop, and why should an ovum fertilized by a sperm start to divide? So I've tried to go into these concepts and explain these questions in the book. It boils down to the second law of thermodynamics and its beautiful interaction with the universe of cells and the biology. So we have come up today with the concept of intratumor heterogeneity, which is what I mentioned in simple language, that there are gazillions of different signatures inside a tumor mass. And chromosomal instability, which means that the chromosomes and genes are not stable anymore, and they give rise to mutations and translocations, deletions, additions, modifications, non-stop. And there's another beautiful concept in tumor mass for cells that are sitting there and cannot grow, and we call it grow or go. Those cells that go, and that it happens really early in this stage of tumor evolution, in the very early stage of many cancers, you have circulating tumor cells. Those are the cells that could not grow, but they are the ones that have gone. And they are looking for a new environment and a new territory, a new organ to basically clone, and they do, and that's what kills the patient. Metastatic cancer many times is what kills the cancer patient. So indeed, we need to find a way to interfere with the evolution of the tumor mass. Tumor mass is constantly evolving into a higher and more complex stage. It's like us as small kids playing with, let's say, Bobby Fischer and playing chess. We get checkmate and whatever we do. However, there might be a way to slow, if not freeze, the evolution of tumor mass and turn cancer into a chronic disease. I think that should be a realistic next step in evolution of our thinking about cancer treatment. Our future generations should come up with a mechanism to turn cancer into a chronic disease. Like, for example, in diabetes, patient takes a pill. Patients that have hypertension take a pill, and they live for many, many, many years. We could do the same thing for cancer patients, and I don't see any problem with that. And I think we shouldn't be too ambitious at this time, because the system is too complex. It's as complex as the evolution of life and beyond. So that's where I see the future of cancer treatment. We are going to turn cancer into a chronic disease by just simple means, maybe perhaps a pill that the patient has to take maybe one time a day. And we should also take ourselves into bigger horizons of imagination as to how to do that. In the book, I have talked about superquantum vectors. What are they? Superquantum vector is a very new model and thinking that I brought in the book. Today we have vectors. Vectors could take one gene into one cell or one bacterium. However, superquantum vector that I'm defining in the book for the first time reprograms each cell in the tumor mass accordingly, according to its entropy barcode, and then gets out of that tumor cell and goes to the next cell the way a flu virus does, and reprograms the key players of the tumor mass in such a way that the tumor mass evolution would slow down, and the tumor would not kill the patient, and the patient would continue to have a chronic disease, live with cancer for many, many years. So we have a long way to go. The thinking that we have today and we had yesterday, that we have to kill the cancer cells, and we have become much more sophisticated cancer cell killers, from carpet bombing, single agent, simple bombs, to multi-agent, complex bombs, to laser guided missiles, smart bombs going into the cells with radioactive material attached to them. Has one thing in common: killing the cancer cell. And I think perhaps it's in the evolution of mankind that killing is considered to, cure the enemy, get rid of the enemy. However, the thinking that has been described in the book is that yes, we could convert bad into good, but we need to understand good and we need to understand bad deeply so in order to be able to do that. We need to go back and take one step back and re-examine the normal cell and the mechanism of normal mitosis before jumping prematurely on deeper and bigger and more complex questions, such as how a cancer cell divides. So I hope I would have become able, by just going very briefly through the last 76 years of modern cancer therapy history, and give all of you a view about what future would be all about. Thank you very much for your time.